Good afternoon, 8th and ninth grade. Are you ready for Module 15? How'd you make out on test? I hope you all made 100. Was it a hard test? I don't think it was too hard. It was pretty easy. If I could, at least if I could see the answers, it was easy. So we're ready for 15. Hey, by the way, there's someone here. Would you like to see who's here? Let me show you back there. Can you see back there? Back there, you got Cody back there. I don't know. Can you see him back there? Where's he at? He's checking hard. He's grinning a little bit. He didn't know I was going to do this, but I told him I was going to put on class so he could listen. So I know some of you come back and check every once in a while, and that's all right. If you want to come back and check, the classroom is never locked. So you can come back if you're in the area, or if you're like Seth here, you can just walk down to the school or bike down to the school and check your work. That's perfectly all right. So I see that we have 2 modules left, and we got a couple weeks left. So that means we're going to work fast. So today I've given you a pretty big assignment. I've given you 2 parts. It's 2 sets of questions that you need to model page 367 to 374. And there's 2 different parts here that's got questions on it. So you'll need to do both of those. But they're pretty easy. It's pretty fun. Yeah, light. Let there be light. You know who said that? Yeah, God. And there was light. You see, it was it's so important. It was the first thing that when God was making the world, He was making things, He made light first. So, you know, it's kind of like that. Anything in life that's important, we do that first. And so, just to give you a little concept of how important light is, God made it first. If you turn to page, the first page, 367, you see that light travels in waves. Okay. Now we just got finished talking about sound traveling in waves, and now we find that light travels in waves. It's a little different though. There's one thing that's different about light and sound. You remember how, and I don't know if you got your test done or finished or not, but you remember on the study guide there was this question about this alarm clock, and if it was in a vacuum, could you hear the alarm go off? And there was that little video I showed you of the phone that was inside the vacuum, and you couldn't hear the phone ring when it was in a vacuum because sound needs waves, air to move. Light is not that way. Light does not need air to move or a medium. It actually moves faster in a vacuum. And we'll talk about that here in a moment. There was a man at the bottom of page 367, you find his name, James Clerk Maxwell. He was a man that said, how can we figure out the way that light travels? And he asked this question, how does it travel? And so if you turn the page, he says that it travels like the magnetic field. So if you look at the figure on 15.1, it gives you an idea of how the waves twist together to form the direction of the light. Now, looking at the picture, you almost think the light is traveling to the right-hand side of the book. It's not. See the arrow? It's actually traveling to the left-hand side. So it's got electromagnetic oscillation, and you got the magnetic field oscillation. So they're twisting into each other, okay? Now study that closely. If you look at the red line, you can see how they twist into each other. Now that is the best example that we can have. We're not saying that it travels exactly like that, but that is close. You have one black word, or one word that's underlined, it's black. It's referred to as electromagnetic ways, and that is one of your study words for your test. A transfer wave composed of an oscillating electrical field and a magnetic field that oscillates perpendicular to the electric field. Okay, so one turns this way and the other one goes the opposite way, okay? So when this one goes this way, this one goes this way. They go opposite of each other. Now, he says, there should be something bothering you at this point. He says, you should be saying, wait a minute, back there, and when we were studying the neutrons and the atom, we studied that light has little protons, little injections of protons. So he says, now what do? You say it travels in a wave, and you say it travels in little segments called protons. Well, scientists today believe that light has dual nature. Okay, it can travel in waves. It can also travel in little protons, little segments. So that really puts it in a tough spot, in a mystical, almost mystical thing. It's really beyond man. You're right. It has characteristics of waves, but it also has little segments like protons. So, can I say it this way? Although it has particular characteristics that just simply can't be explained. We just can't explain them. So now we'll move on over to page 369. We have the quadrant mechanical theory of light. Okay, you see it's a theory. We know that theory is not necessarily something that we can prove exactly the way it is. So, while we have this wave, it's kind of broken up in little particles as well. It's not a solid connection like this, or a solid twisting like this. It's little particles passing as well. Wow. Does that sound a little confusing? It is kind of confusing, but it's just the best that we know. It's the best that scientists can explain. Scientists just can't tell you exactly how light travels. Now let's move on to the next section there at table 5.1. Now one thing about light, we do know that it goes fast, really fast. And so you boys, you love this here. There's always this thing that is a topic of discussion. The fastest car, or the fastest plane, or jet, or all the way down, even who's the fastest runner. It's just in boys and some men too, okay? What can go the fastest? So we have a race. We have a running race. We have a car race. I don't know if they have jet races or not. They have semi-races. I know that. We want to see how fast. Well, let me tell you the fastest thing. Okay? Light, the speed of light, is the ultimate speed limit of matter. There's no car that can go faster than light. There's no other portion of matter. Matter of fact is you can't go faster than light. Don't even try it, okay? Look at your table on page 369, table 15.1. Now let me back up and do just a little bit of review about sound. You know that sound went so fast in air, and the warmer the air, the faster it would go. And then when it hit water, it would speed up. And then when it hit a solid like steel, it would go whee! I mean, really fast. Well, light is the opposite. Oh yeah, sound wouldn't even travel in a vacuum. Light's the opposite. It goes the fastest in a vacuum, faster in air, and then slower in water, and the slowest all in solid. Or in a liquid, I should say. The fastest in light goes the fastest in a gas or air. Next is a liquid, and last of all is a solid. Well, that's not too hard to travel, I believe. I mean, if you want something real black, real dark, you put a wall there, and then the light don't come. Well, sure. You got your list there. The speed of light is 300 million. Is that right? 300 million meters per second. It's better said that it's about 670 million miles per hour. 300 meters per 300 million. So it's 670,000. No. 670 million. There we go. 670 million miles per hour. Sound travels through air at about 340 meters, or about 760 miles per hour. It goes through vacuum a lot faster than it does air. Air is 760 miles per hour. That's still pretty fast. I mean, yeah, 760 miles per hour is pretty fast for sound. But light goes 670 million. Yeah, I think I'll just turn the page on over. If you look at on your own problems, that first one, remember I told you about light, how it's passed. I'll give you a little hint. It's twisting and sending little particles. It's traveling in a wave, and yet the waves are broken in little segments. Does that give you a little hint of which one you're going to choose there? And also, it travels the fastest in a vacuum, the next in a gas, the next in a liquid, and the slowest, the next in a solid. So light is exactly backwards than sound. All right, I told you I'm going to give you a little bigger lesson, so we'll just keep going. On 370 and 371, you have an experiment. If you do the experiment and you work on that one, if you do the experiment, I will let you skip number 15.3 in your study guide. Or no, on your own problems. It's on page 374, the first one. I'll let you skip. So if you don't want to do that problem, you do the experiment. And it shouldn't take a lot of work. Be sure though, I've got a little bit of advice to try to help out your mom and dads at home. Be sure to follow the last step, step number 7. If you do the experiment, you must do step number 7 to get the credit for it, or to skip. If you do the whole experiment and don't do step number 7, I won't let you skip 15.3. Ha, I got you. All right, look at the light of the rainbow. In the picture on 15.2, the wavelengths of light, you see you have the colors of the rainbow magnified. You have red all the way over on the left, and you have violet over on the right. And in between there, you have all the others. Now, take a little note of that abbreviation is NN. That's nanometer. It's a billionth of a meter. A billionth of a meter. Now, a billionth of a meter. Did you get that? I don't understand that. That's too tiny. A billionth of a meter. That's how different there is in color. A billionth of a meter difference in wavelength. So it kind of makes sense. If you stop and think about it, you will never see the red on the inside of a rainbow, okay? You know why it bows? Because the red has longer wavelengths than the violet. Now, let me tell you, and we're going to get on this a little bit later, you will need to know which one has the longest wavelength. So if you can picture a rainbow, and I'll just quickly turn over the page, you will see it over on the next page on 372, but you have the highlight ROYGBIV. If you remember in one of your other science classes, I'm sure you had this, it's Roy G. Biv is the color. And there's other sayings as well. I was trying to think of some of them here this morning and I couldn't think of them, so I'll just stick with the one in the book. Roy G. Biv are the colors of the rainbow, the first letter of Roy G. Biv, ROYGBIV. And that will tell you. And remember, it starts out with the longest one and ends with the shortest one. So any point in time you can just, oh, I know, just simply write them out and you just put the letters and that will be your colors, and you know it starts with red. Red's on the outside of the rainbow. Red's on the outside. Indigo is on the inside, or violet. No, indigo and violet are on the inside. Now that's important, okay? I'm stressing this here because you want it for test information. Now look at page 372 on the bottom. You see electromagnetic waves are smaller than light and bigger than light. And if you can understand that infrared, if you can understand that electromagnetic spectrum right there, and just look at that and look at that and study those pictures, that is so vital, so important to understand light. Okay? You see the visible light and about in the middle of the page there. You have visible light. So put your finger on that. Everything to the right, those waves you can't see. Everything to the left of that, you can't see either. Okay? So of the wavelengths of the electromagnetic waves that we can see with our naked eye is, oh my, just a tiny portion. So, just start backing up. You go to the left. Okay, if you're looking at your book, you go to your left, and you have ultraviolet rays. Okay, that's like sun rays that are giving you a tan. If I would say what that little bottle is, I'd say it's tanning lotion. And then you go a little bit farther, and you have X-rays. That's when you put your hand out, and they take a picture of your hand, and you can see your bones. X-rays will show your bones if they want to know if they're broken. And then if you go far enough over, you get the gamma rays. They're just wee little. Okay? Now flip it the other way. From the visible light, you have infrared light. Now you can see a little bit of infrared. There's heaters. If they put out heat, like there are little infrared heaters or electric heaters. There's space heaters. They heat up and they make a red glow. Okay, you can see that one. But it is just way over on the edge. See, it's just past the visible light. So it makes only red. Then the next is microwaves. When you put stuff in your microwave, well, you know how it is. I can't see that light flashing in there and heating up the hot dog or the sandwich or whatever you heat up. Next is television waves. You have to have a television to accept those waves and put it in the picture, because I can't see those pictures flying through the air. You can't either. And worse yet, it's radio waves. Someone talk on the radio and you can hear them down the road. They'll talk back to you, or you can go to the radio station, whatever. You can't see words flying through the air. But mind you, those waves are going. But they're long ways, okay? But what we can see with light are here, and if you go below light, they're short, and if you go above light, they're long. Get that concept. You see the little ziggy-zag line above there? Don't just look at that and say, oh yeah, I got it, and go off and go fishing. Get that good. Get that good. Yeah, you enjoy your lesson. I'll catch you later.